I think let's get started. Hopefully you're all okay with this being recorded. I just did want to preface that this will be uploaded unlisted to YouTube for future reference because Zoom deletes recordings, I think, in 30 days. So if you're all good with that, please let me know. If not, you can probably change your name, meeting, or don't turn on your camera. But yeah, with that out of the way, I think we should get started with a quick opening remarks to introduce the students and the cohort. And then after that, we'll get on with the presentations. Really quickly, I did want to share, we're a little bit behind schedule, but that's expected. I did want to share into the chat the symposium schedule. So this includes who's presenting what, who's presenting when, etc. Before each of the presentations. Each of the students will introduce themselves, etc. So you can get to know who the students are, as well as what they're working on. Cool. So with that out of the way, I think it's time to welcome the 2024 Summer Blast AI Symposium. I'd like to congratulate all of our students and welcome everybody else who is here in the audience. Students, if you don't see your parents, definitely send the Zoom link in case they didn't get the email. But hopefully everybody is excited to be here and is ready to hear some presentations. I'm sure the students can't wait to share their novel architectures, robust methodologies, and exciting findings. But in Blast AI tradition and in the spirit of empirical research, I'd like to introduce the 2024 summer cohort with some numbers. So in front of you, you have 32 Blast AI students presenting in the research cohort. There were in total 444 total applicants. They sat through 50 hours of lectures and they still had the energy to send thousands of messages in the Slack and conduct advanced research in the remaining 6 weeks. Each student here began the program by completing an intensive bootcamp on machine learning. I really do mean intensive when I say intensive, because throughout the bootcamp, they've delved into a lot of state-of-the-art research and techniques that you often wouldn't be able to find in a textbook because they were just released on archive a few months prior. Much of the material is recent and advanced and prepared them for the next section, which we're here to celebrate. That's the research program. During the research program, which was the next 6 weeks, each student began working on an original research project along with 6 teammates under the guidance of a mentor. I'd like to take this moment to recognize our amazing and exceptional mentors, Ian, Bohan, Osher. You were all amazing. For context, they are research scientists at Luma AI, Berkeley Artificial Intelligence Research Lab, and KIC. Without them, this summer would not have been possible. These mentors worked effortlessly. And when I say that, I really do mean it. These mentors put in the time, they put in the effort, and they really did everything to make sure these students were guided towards exceptional research outcomes. It's important on that note to mention that the projects that you will see today weren't just toy assignments with expected outcomes and copy-paste code. These were real projects. Each of the mentors helped guide the students towards PhD level research that builds upon the most recent advancements in the field. It's important to note that these projects were difficult, and you will see that as you see the presentations and the challenges and ultimately the successes. At the beginning, the students read countless related works. They spent hours reading through related repositories, PyTorch documentation, Hugging Face datasets, you name it. The process was full of bugs, and many times results initially didn't go their way. But despite everything, the groups pushed forward, and the fruits will be shown today in the symposium. By far, the 2024 Blast AI Symposium is full of some of the most resilient individuals you will ever meet, who are driven by academic pursuits and a desire to understand how the world works and how to make it better. The presentations you'll see are the products of hours spent reading, coding, and innovating. One thing that we always like to say at Blast is by the end of the program, you're not just a student or a high school student, you're a researcher. And hopefully today, you will be the proof. The presentations We'll go in the following order. First, we have advancing super resolution and neural radiance fields via variational diffusion strategies, followed by improved multimodal deception detection using graph convolutional networks, followed by streaming pitch estimation using informers, and enhancing LLM conversational acuity using pragmatics measures. I just said a lot of words, and I'm sure you're excited to hear not from me, but from the students. And students, I hear you. I understand you're excited to present. And with that being said, I'm very excited to welcome the first group, which is all about advancing super resolution and neural radiance fields via variational diffusion strategies. A lot of big words that they'll hopefully unpack. Shrey, are you ready to share screens?
Yeah, I'm just gonna share my screen.
Excellent.
Are you guys able to see the slideshow? Okay, that's good. So our paper that we worked on in this program during the summer is essentially advancing super resolution in neural radiance fields, variational diffusion strategies. That's like a lot of big words, and we're gonna unpack, what each of those are, like neural radiance fields, what's variational diffusion, and then yeah, super resolution is essentially like taking something that's low resolution and upscaling it to a high resolution. But yeah, I think we're ready to get started.
Okay, so first, what are nerves? So a nerve stands for a neural radiance field, and basically it's a 3D model created from various 2D images from different angles, and it's a machine learning model that is trained on different pictures. And what it basically does is it predicts the color and a density of the color at various pixel values. And it's able to do this by shooting, you can see in the picture on the bottom, this red line that goes through the machine is like you can think of it as like a imaginary laser that goes through the picture, and it calculates the color and density at each point. Um, so the model is trained on the color and density and minimizing the difference between what it generates and what is there in real life. So that's what a nerf is and how it works. Yeah. And so what are the challenges today with current models in 3D vision? So the first challenge is resolution, and it's difficult to maintain high resolution during rendering. So, if we see something in real life and then convert it to 3D via nerfs, a lot of the fine details can be gone, and this can cause blurry models. And there are also issues with consistency. So with a lot of different viewing angles, you can lose details, and it's hard to stay consistent. I can have a consistent image with a lot of different viewing angles from different positions. And really complex nerves can take a lot of computation, and there's a lot of resources required. And if you can get these resources, you will get lower quality and higher runtimes.
So our goal was essentially to optimize nerf editing and nerf super resolution with something called variational score distilling. So in a nutshell, we'll go over this later, but variational score distilling is essentially a method. It's like a loss score that uses fine tuning to uh, better create high resolution images that are also consistent across viewpoints and also preserve high quality details. Yeah, so our goal is essentially improving 3D models generated from 2D images using neural radiance fields. Lots of applications such as in VR computer graphics and 3D imaging, where you need, high quality three-dimensional models, but you might not have the computation for it because you need to render it in real time. And then certain new, renoise score distillation, a new method that was introduced, I think, start of 2024 this year, does very well on this benchmark, but we were able to show better results than RSD in terms of model quality. So in terms of the methods used to enhance nerfs, we have three things in our methodology. The first thing that we already discussed is the variational score distillation loss function. The reason we use this is to minimize divergence between our pre-trained model and our model being fine-tuned. And the reason this is better, rather than training our model from scratch on the images, is because it's better generalization and faster convergence than certain techniques like score distillation sampling, which is an old technique that's been used to generate 3D nerves from text prompts, and also, the newly introduced Reno score distillation. And we also use something called low rank adaptation, or LoRa, So the reason we do this is because generally the models that we're fine-tuning, they're really, really big models. So we don't want to fine-tune the entire model because that requires like a lot of compute and is infeasible, with the amount of compute we had available. So to get past this, we use what's called low rank adaptation, or LoRa. So what LoRa essentially does is it takes like the weights of a certain model and it breaks it down into smaller matrices that can then be trained in part along with the frozen pre-trained weights. And we essentially use LoRa to fine-tune our super resolution models, which led to high resolution rendered NURBS when we were actually rendering our NURBS using the latents. And then one thing that we kept the same as the other papers is iterative dataset update, or here we call it iterative 3D synchronization. This is a very normally used technique when we're dealing with changing the data in NURBS. It essentially, what it does is it alternates between upscaling and 3D representation refinement. So it upscales, then it syncs the data, upscales and syncs the data, and we do this continuously in a cycle. And that's essentially what iterative 3D synchronization is. So now we're going to talk a little bit about the variational score distribution distillation process. So VSD essentially reverses the forward diffusion process in NURBS. So what that essentially means is you have your rendered images, and what you're doing is you're adding noise to them. And the goal of the model is using your VSD score to predict, what the added noise was, so it can remove that noise. And this essentially leads to better details in the model. And the process is modeled by like a SDE equation that you can see. So you have your this is essentially like a differential equation that describes the process. And then the reverse diffusion essentially utilizes a score-based model, and our score is like all the way on the bottom. And VSD in a nutshell works by having a pre-trained upscaler along with an upscaler, which is essentially a copy of the pre-trained upscaler. But then we take that upscaler and we insert some LoRa layers into it. And that's the things we're fine-tuning. And then, yeah, the LoRa upscaler takes in an extra parameter. So I'm just going to go over a little bit on the equation. So the loss function is essentially the prediction of the pre-trained model given the input image, the time embedding, and the condition, which has some sort of like label on it, and subtracted by our fine-tuned model, which has the image, the time embedding, the class label, and the condition.
Okay, iterative 3D synchronization. So basically the biggest problem with 3D models, when you're looking at a 3D model in one specific view, you might not notice any details gone. But when you switch to a different view, maybe looking at it from a side, you'll see a much lower resolution. This is what iterative 3D synchronization does, also known as I3DS. So basically during the nerve training, after the upscale, what it does, it goes back to the refined, and it makes multiple copies. And each time it runs through the upscale, the resolution gets higher and higher. And so what this does,
Oh yeah, my screen froze up a little bit. I think it's because of like my internet. All right, that should be good. Oh, yeah.
okay. So I was saying, so each time I3DS runs through the nerf, what it does, it improves the quality each time it runs through. So basically, during like VR games or AR games, and even during movies, when there's more consistency, it leads to better consumer being immersed in their entertainment. And so this means a higher resolution means the model performs better.
So now we're going to talk a little bit about how low rank adaptation works. So LoRa is, I think, like state of the art when it comes to fine-tuning model, like upscaler models, or honestly any sort of model, like lots of LLMs and lots of diffusion models. You can fine-tune those with low rank adaptation. And it's a balance essentially between like adaptability and computational efficiency, because it doesn't require like a lot of compute to fine-tune the model. And how we essentially do this is we have our pre-trained weights of the model, which we freeze. We just keep those there, and then we introduce a rank, which helps us create a two smaller matrices in this case, which we call A and B, which lowers the amount of weights that we need to fine tune. And then what we're essentially doing is we're combining our weights along, which are frozen. So our W here is frozen in the equation, and our A and B are the things we're fine tuning. And then our new weights is what we're using to actually perform the computation. And then this is like the gradient for it. So like our loss with respect to like the first matrix is essentially our gradient with respect to the weights times B, which is basic like gradient descent, and then we do the same thing with our other matrix, and then we just keep updating these until we think that our fine-tuned model is good enough, and then we essentially fuse the weights back into our and we get each of their outputs and we combine that into a singular output, which is like our actual output of the model.
All right, so this is like the outline of our entire model. We start off with a low resolution nerve with which is created from the images, and you take the render and you interpolate it to a 4 times size, so you make it 4 times larger in a higher resolution. And then using an encoder, you convert it to latent, which is an easier form for the model to process, and it allows it to apply VSD. And before we can apply VSD, we have to add learnable residual latents, which are basically latents that we can edit and change. And with VSD, we can increase the quality of the model and make it more realistic. And then we can decode these the learnable residual latents and make it renderable and higher resolution. And we can use iterative 3D sync to update the nerve with the upscale renders. And then we train the model again and again till we find a 3D model we're like satisfied with.
Yeah. So yeah, it's just basically two things being trained are the learnable latents and our LoRa parameters.
So experimental setup, we use an LLF dataset. So basically it's just a dataset full of 2D images, and the model reconstructs the 2D images into a 3D area, 3D model, sorry. And then with this dataset, we can test the model's ability to handle complex textures, lightings, and other details. Our performance metrics, so we have L1 loss, which measures the average difference between the predicted values and the true values of models, which gives us the overall accuracy of the model being able to reconstruct 3D models. MSE measures the average squared difference between predicted values and true values, and MSE weighs larger errors more heavily than L1 loss does, and it's useful for showing big deviations in different types of models. SSIM evaluates the quality of images between the original model and the reconstructed images. So this basically helps show us the visual quality and how the human eye would actually perceive the 3D model. Finally, PSNR is a test that compares the maximum possible pixel values of an image with noise. And this means the higher the PSNR values means the higher quality of images that we have. So our comparison methods, LPIPS and NIQE and PSNR is what we tested. All of those help us understand how how a human eye would actually perceive the built model.
So now we're gonna go over like the results and analysis we got. So in terms of comparison with existing methods, the state-of-the-art method is like DISR nerf, which uses ID3S and plain RSD. So this is like a table of our tests. So in terms of the first benchmark, which is LPIPS, plain RSD performs a bit better than our two current methods. So in terms of the human eye, that means it would in some cases look a little bit better, but we're still very close in being able to match that benchmark. But in terms of the other benchmarks with the Nikkei and PSNR, our model consistently performs way better, especially the VSD plus LoRa outperforms both VSD and plain RSD on both of the benchmarks. So essentially, in a nutshell, our techniques do better on 2 out of the 3 benchmarks, which shows promising results compared to state of the art. And in terms of improvements that we're thinking to better match the LPIPS, we're thinking of adding some sort of loss score that helps the model, also take LPIPS into account in a more direct way rather than us being able to indirectly train the model and improve LPIPS. So those are some techniques that we're thinking of trying out.
Here is the output when we use renoise score distillation. Now we can see it falls short in output quality and takes longer training times. Here is the output after applying variational score distillation. It is evident that the model quality has improved with a more efficient training time. Here is what the output looks like after low rank adaptation used to fine tune it further. And here is a 3D video showcasing the same.
All right, let me play it. So this is like our 3D nerf output with VSD and LoRa. We trained it on 10,000 super resolution steps and 20,000 synchronization steps, and we got these results. And I think it took around 4 to 5 hours to train, which is a little bit more than RSD, but you know the visual quality makes up for it. But yeah, let me go to the next slide.
So future implications. So basically, with the integration of VSD, I3DS, and LoRa, we have significantly enhanced the quality and consistency of current nerfs. And with the use of new benchmarks and qualitative and quantitative benchmarks, instead of RSD, it shows more superior results. This can be used in film production and gaming. In film production, for example, in Interstellar, the black hole scene, that film is known for its black hole scene, and that scene was created by hundreds of computers, and it took many hours to complete, over 100 plus hours to complete. And so this study could actually increase efficiency and it can increase the resolution. In gaming, it can be used in applications such as virtual reality and augmented reality.
Yeah, so that's it for our presentations. Now we can take questions from the audience.
Everybody, if you have a question, just please raise your hand, and we'll just go from there. No worries if you need to take a second to gather your thoughts. This is really advanced stuff. Yeah, Shravan?
Yeah, I was going to ask whether the improvements that you have seen, have you reached the limits or can you improve further?
So with the amount of compute and time we had, we weren't able to train it on the maximum number of steps. Just because of the lack of like we didn't have like infinite resources. But I think we believe if we keep it going, I think our results will kind of plateau. But yeah, I think we can still kind of improve our results if we train it for longer durations of time.
I was just curious, I mean, what kind of compute you had? Did you have any A100 machines to run on?
Yeah, so we had I think an A10 and an A100 server to run our code. But yeah, nerf stuff is generally really computationally intensive. So even on those machines, it took a lot of time. Yeah.
Thank you.
This was a really great presentation. One question that maybe some people are wondering, that I'm wondering is, can you explain the different benchmarks? You mentioned 3. What are, I guess, the different things that they check, and how can they qualitatively measure whether things look better or not?
So the LPIPS, also known as Learned Perceptual Image Pass Similarity, it basically measures the perceptual similarity between the images we gave in and the 3D model that it gave out. And it basically uses a other trained data set on the cloud, and it compares them to see how humans would actually perceive it. So for example, on the table, the lowest score is the better one. We didn't do as well, but we're looking to improve that. The NIQE, Natural Image Quality Evaluator, is basically an assessment that evaluates the naturalness of the image based on other natural scenes from its data set. PSNR is basically, it measures the image quality, like resolution-wise, from the previous images, the 2D images that we fed in, and whatever 3D model we got out.
Awesome. We have a question from Lox.
Yep. Could you talk about what kind of data cleansing we did? Is the data was already pre-cleaned, or do we need to clean the data initially?
So in terms of the data, there were like already pre-made data sets that we used. So the ones we used is like the LLF Horns data set, which is like I think 62 images of like I think like dinosaur fossils in like a museum, and they took pictures of that. So we didn't really have to like do any sort of data prep. I think the only thing we did was we just decreased the size of the image, and then so because like the images like came really big, so to like, kind of conserve compute, we downscaled it by 8x, and then we upscaled it by 4x when we were actually doing like the pre-training. But yeah, we didn't have to do too much with dealing with the data. It was mostly about producing our NERF representation.
This was incredible. Very clear that all of you know your stuff. This was an amazing project, and hopefully if there are any additional questions, we can maybe ask in the chat, and hopefully you guys will also be around. I think it's time, because we are running a little bit behind, to move on to the next amazing project. This one, the title is Enhancing Lie Detection Accuracy, a comparative study of classic ML, CNN, and GCN models using audio-visual features. Akshaj, I believe you should be ready to present. Let me know if it works, and thank you to the previous group.
All right, give me 1 second. Okay, can you see my screen?
Yep.
All right, good.
Yeah, this is multimodal deception detection with microfacial expressions by Adwait Me, Akshaj, Ayan, Abdulrahman, Arnav, Daniel, Troy, and Ryan.
Yeah. So let me walk you through what we'll cover in today's presentation. We'll start with the introduction, where we set the context for our work. Next, we'll review previous works to understand the landscape of existing research in this area. Following that, we will dive into the methods we use to develop our model. And after that, we'll present our results, showcasing the performance and key findings. And finally, we'll wrap up with a conclusion, summarizing our insights, and discuss future directions to explore how we plan to build on this work. So let's start with the introduction to set the stage of a presentation.
Okay. The idea of lie detection has been really popular for humans because as human beings, we frequently lie. And this has been a big thing for law enforcement and criminal justice for hundreds of years. But the main method that has been used are polygraph tests, which set to measure your human activity through, for example, blood pressure. There's also fMRIs, which measure the blood going to your brain. But all of these techniques are very unreliable. Some studies find that they're wrong almost 50% of the time, generating false positives. The idea of machine learning is to present a new avenue for lie detection that's not invasive. You don't need to attach any wires to anyone, and you can do it after the fact. All you have to do is record them when they're saying something. There's also significant concerns about human rights with lie detection, because frequently when lie detectors don't get the information they want, they resort to torture, which is why this is such an important field.
So focusing on the research questions, first is how effective is a proposed AI model in detecting lie compares to traditional methods and some recent AI models? And second, which combination of audio, visual, and gesture features provides the highest accuracy in the lie detection task? But before we head to actually answering these questions, let's examine some previous works of research that has been conducted on this topic already.
Right. And so overall, we're going to examine some previous works that concern lie detection using AI and ML models, and especially 3 aspects of those works that will be integral to and relevant to our methodology and how we try to innovate over those papers. And so first would be text and speech analysis. And it focuses on detecting deception through linguistic cues and vocal features. And it also analyzes aspects of content, vocal delivery, tone, timbre, those ums and ahs and hesitations that are almost pinpointing a person's lying or behaviors. And second is the most almost state-of-the-art feature, which is microfacial expressions and facial analysis. And so these are involuntary twitches or behaviors of a person that can often indicate deceptive behavior. And there's also semantic classification using gesture aids, and those increase accuracy dramatically. And then finally, our approach to this is using a whole picture method, a multimodal approach. And this involves integrating multiple different data inputs, as many as we can to find a whole picture method. And so that would be audio, video, and transcription. And in our case, transcription would be notations of gestures that a person does in a video, and microfacial expressions as well.
A previous study named Box of Lies Multimodal Deception Detection in Dialogues. Its main idea is to examine the use of multimodal techniques to detect deception during conversations. Key focuses first, analyzing the combination of verbal and non-verbal and the dialogue feature and achieving accuracy of 69. Another key focus represent non-verbal behavioral features as percentages of 1 minute to align and combine features. Another study is deep neural networks for lie detection with attention on biosignal. Its key focuses are two forms of data: facial landmarks and the mere frequency. Another one, they trained their model as a DNN, deep neural network. The third one, accuracy report of 98, but they mentioned that the existence of an accuracy paradox, meaning the model is much less accurate in reality.
So before diving into our approach, it's important to understand the limitations of the current methods used in lie detection, both traditional and modern. So let's talk about faulty polygraphs. So when we talk about traditional polygraphs, there are several significant issues. First, people can sometimes slip through undetected, which questions their reliability. Anxiety is another big factor. It can lead to false positives because the test might pick up on stress rather than deceit. The interpretation of polygraph results is also highly subjective, which means two experts could see the same results differently. All these factors make polygraphs less reliable and not universally applicable. Now let's look at some of the challenges with current machine learning solutions. A big problem is that many models struggle to function well across different data sets as they don't generalize well. Many of these models are prone to overfitting, meaning they work great on training data but falter in real world applications. Real time lie detection is still not accurate enough, and there's always a risk of bias creeping into the models. This makes it difficult to generalize these solutions to a broader audience or different cultural contexts.
So our goals consist of detecting and analyzing facial microexpressions to detect deception accurately. And we want to implement a audio or speech and video encoder, such as OpenSmile for audio and like CNNs for video. And this is to increase interpretability and generalizability, which is something that previous papers have struggled with. And this is also to create an accurate representation of a data set. And we want to use all of this to achieve a higher accuracy than current machine learning models and polygraph tests, as we want our model to showcase a way to detect deception non-invasively using our dataset and using a classification model. Next, we have the methods that we use to.
And so now let's get to the meat of the problem, how we are trying to solve and innovate over different other solutions. And so first, as you can see in the deception detection pipeline graphic, our data is a multimodal data set, and it's via the University of Michigan real-life trial data set. And so our data set consists of videos, audio, and handwritten annotations, and they describe different movements, mannerisms, and like obviously microfacial expressions. And so we analyze those using heat maps and kernel density KDEs. And as you can see in those two graphs on the right side, we can make conclusions off of those and to see which aspects we have to drop because they're not relevant. And so in the heat map over there on the right side, the color graph over there, we isolated the aspects that have less relevance to the class determination. And so we could drop those aspects because they aren't relevant to lie detection. And then finally, we have the KDE over here, which is the graph. And as you can see, the two aspects match together exactly the same for each class. So that's 0 for truth and 1 for lie. And since they are the same and don't have any differences, we can drop them because they don't help us make that determination or help the model make that determination. And so as far as the pipeline goes, for audio, we use OpenSmile, which is a amazing tool to process audio into something that's interpretable. VIT is a vision transformer. And then we use interpolation as well, which is a strategy to find the values through estimation between known data points. And it makes us possible to not miss any data and concatenate properly. And so after we combine all three features and experiment with those, we transition to testing out our models. And so here are the models that we find relevant to the task at hand. And they have all different strengths that we will explain later. But first is a CNN LSTM. The second is a CNN convolutional one-dimensional network. And you can see that's highlighted over here because it's our best performing model, as we'll get into later. And then there are some classics like logistic regression and random forest classifiers. And then some new, more state-of-the-art experimental models, like a graph convolutional network and film, which are more new applications to this kind of task, which is lie detection and binary classification.
And here we're talking about audio and video processing. Like you mentioned earlier, we're using OpenSmile, which is an open speech and music interpretation by large space extraction. And what it basically does is it takes a pre-processed audio features and extracts stuff like sound qualities that can be pitch, formants, or even loudness, and other voice quality features such as shaking and other things that could potentially indicate lies. And next is the VIT, which is the vision transformer. And what this vision transformer does is it basically divides images into smaller patches, which are usually 16 by 16 pixels, which are then flattened and turned into vectors to run through the vision transformer. And from this, we can extract other features from images and videos that we can use for more understanding of lies and feed into our models.
So now that we're done with our pre-processing and extraction of features, we had one more step before concatenation, which is interpolation. So our VIT features had to be interpolated so they match the 50 Hertz sampling rate that was there for OpenSmile. And this allowed VIT to be combinable with the OpenSmile feature vectors. After that, we concatenated our visual features from VIT, our audio features from OpenSmile, and our manual annotation gestures in a channel-wise concatenation method, which would give us a combined feature. So before we get into how our models worked and training our models, I want to quickly go into how we split our data. So for our project, we use k-fold cross-validation, which is a method of avoiding the overfitting of data to a model. And overfitting is basically where the model is too much adapted to the training set and not as well adaptable to the test set. So we use 5 k-folds. And what this means is that we split the total data into 5 different chunks. And each time we assign one of those chunks as the test set. And so for each iteration, we found the performance on that test set, keeping the other ones as the train set. And we repeated that for 5 different times, rotating which one's the test set. And at the end, we found the average accuracy of all our 5 iterations.
Now we'll go over some of the models that we used to run this. The one that was the most successful was the CNN, or convolutional neural network. We used a one-dimensional convolutional layer to extract features from the data, followed by dropout layers to again prevent overfitting, which is a big problem with this area of machine learning, and then batch normalization to stabilize and speed up the training. As we talked about earlier, this is a multimodal approach, which means we use everything, including audio, visuals, and transcriptions, which is the text of what they're saying, and gestures. But then we also wanted to think about what happens if we don't include the transcription. There are two reasons for that. One of them being that the transcriptions might not actually help improve the accuracy, because when you transcribe what someone's saying, you don't really get the ums and ohs. You just write down exactly the words they're saying, but you don't get the filler that might describe a lie. And the second reason is that the data set that we used from the University of Michigan had everything already there for you. But if you wanted to do real-time lie detection, then you don't have a transcription there. All you have is the audio and visuals. So we wanted to see what the accuracy would be like if we did not include transcriptions. Lastly, we also tried the CNN and long short-term memory network. This is a model architecture that has the CNN model for the input, but then also this LSTM model to process input time steps. And we wanted to see whether this would do better than just the CNN.
In addition to the usage of CNN, we used the following models: logistic regression, random forest classifier, graph convolutional network. The following are some bullet points about each one. Let's start with logistic regression. It utilizes a sigmoid function, which is good for binary classification. Also, it has elastic net regularization. Third, simplicity and interpretability. The fourth one is baseline performance. Logistic regression is a baseline performance due to its simplicity. And all that is good when afterward we use deep learning. So when making a comparison between logistic regression and our deep learning models, we can determine whether whether increasing the complexity is a good thing or no. For random forest classifier, it is an ensemble model that chain multiple decision trees during training. Third, we add regularization in the form of an out of bounds validation set and limit the depth of the forest. Third, handling nonlinear relations. Fourth, insight on important features. The last one, which is graph convolutional network, GCNs, use the inherent structure of the graph to combine and process different features associated with those nodes.
Right. And so to evaluate the success of our model, we found that simplicity is key because it aids in the factor of interpretability for our results. And so the models are tested on average accuracy for all validation folds, as mentioned previously. And then a classification report is used to interpret bias of the model. Because often, as we said about overfitting, bias occurs when one class is favored over the other, and the classes would be predicting a lie or a truth. And so recall is our first metric, which it measures the rate of false negatives or the completeness of a model. Precision is a measure of how consistent the results are when repeated and the accuracy of classifying a lie. And finally, F1 score is a harmonic mean of precision and recall. Now, these aspects are generally very abstract, but to kind of ground it in our task, I can explain that high recall, if you have a high recall number, it means that there's a very low number of false negative results. And that means that the model does not falsely label results as the truth. And so high precision indicates high consistency rate for results. And these are instrumental in ethical lie detection, and that being an instrument in a real world setting, because failure and misclassification isn't an option when it comes to ethical problems and applications in a court or in law enforcement and etc. And then finally, as far as we are classifying and iterating over the model, binary cross entropy loss, also known as a log loss function, is used for binary classification tasks in general, and we are using that for our models as well.
So these are the results sections, and we are going to talk about what insights we pulled from our models, what they resulted in. So first, let's go over the accuracy of our models. So the average accuracies are listed below, and you can see that the CNN model with the visual, audio, and transcription features performed the best for us, having an average accuracy of 95.4%. You can see that we have listed some hyperparameters below. The first is the learning rate, which is the step of how our model optimizes. And there's epochs, which is the number of times training data was fed through the model. The batch size is how much data was fed through in each forward propagation, and then 5K folds was used for a data split as mentioned. We also want to point out that the CNN model without the transcription features performed with an accuracy of 94.4%. And so this is substantial because this is only 1% behind the CNN model that had the transcription features. And we emphasized before too that a big part of it is generalizability. And with just visual and audio features, having that level of accuracy proves that it could be applied. And this is advantageous because now a human does not have to go in and input additional annotations like facial reactions or something because they already achieve a high accuracy without that information. We also have logistic regression at 74%, random forest at 71.2%, and GCN had only a 50% accuracy, which is in fact less than the human accuracy average, which is 54%.
And so here is the graph for our results. There are 5 columns representing the 5 different trials or experimental runs, and each trial consists of an instance of a model evaluation. And within these trials, we can see that it consists of our 5 different folds, which are the 5 different colors. And what we can see in this graph is that the average of the 5 folds within each trial has very little variation across the entirety, which means that there's very little very little changes in experimental conditions that can hardly affect the model at all. And this indicates a very high precision because across these 5 trials, there's not really much of a difference.
As you can see here, there is a table of all these statistics in a classification report, and this step is instrumental in coming to conclusion about which model is better for our dataset, and also which can be used in a general manner. So previous papers achieved a high accuracy, but they failed to satisfy the aspect of generalizability. And I know we keep using this word a lot, but it is instrumental. And some trends that we can see in this table is that random forest and logistic regression both performed very similarly, as both models had an F1 score of 0.834 deception. And also both models had a precision for deception with 0.77 and a recall of 0.91. And basically this indicates that these models are quite accurate when they predict deception and are also good at capturing most deceptive cases. And the model with the that performed the best overall with the highest precision, recall, and F1 score was the CNN model, both with video, audio, and transcription. So these models had an F1 score of 0.95 for both deceptive and truthful classes, with a precision and recall close to or at 1. This means that these models are very reliable and they made correct predictions almost all the time without missing any significant number of true cases. And lastly, we have the GCN model. Now, the GCN model shows a perfect precision of 1 for deception, but it has a recall of only 0.07, leading to a very low F1 score of 0.14. And this confirms that the GCN is heavily biased, meaning that it is very accurate when it does predict deception, but it misses nearly all the actual deceptive cases, making it unreliable for the real-world application and use.
This graph shows where is our model from the previous one. The first one, which achieved 60% accuracy, introduced a deep local holistic network for micro expression recognition, comprising 2 subnetworks, HCRNN and RBRNN. The second study key components includes the use of CNN for feature extraction and a GRU-based RNN for sequence learning. The model achieves approximately an 82 accuracy. The third one, they fused the CNN and the support vector machine. They got 58 accuracy. That is computationally high cost and low accuracy. And the last one is here. Paper's the project average accuracy is the 95. XAI stands for explainable AI. We used it to show interpretability for our model. First, we use SHAP to interrupt the CNN Conv1D model. Using simpler models allow for more interpretability and customization as well. Audio feature is 3925 and 4054 were identified to be the most impactful feature as shown from this graph. Another explainable AI technique, we use the LIME, and you use a sample for truthful and a sample for deception. From all the mentioned explainable AI figure, the feature 3925, feature 4054, 949, 3672, 2656, 4835, and 5802 and 5882 are the most critical feature, and they are related to audio. On the other hand, feature 6827 is related to visual that were extracted from videos.
Next, we have our conclusions. So our insights, we're proud of our high accuracy that we achieved with the CNN Con 1D model that achieved 95.4% accuracy. And this showcases the effectiveness of multimodal feature extraction. With audio, where we used OpenSmile, and for video, we used Vision Transformers. And we still had a high accuracy without transcription with 94.4%, which showcases our model's strong generalizability. And previous papers lack in this section with generalizability. And our model was able to do this due to a multimodal approach where we combined both audio and video and transcriptions, and this provided a robust framework for lie detection, improving over traditional and recent AI models. However, we did have one limitation, which was our dataset. Our dataset was kind of small with 121 videos, and this highlights the need for a larger, more diverse dataset, which would allow for higher accuracy and generalizability. And next, we have some future directions that we're looking into. So as I said before, we're looking into higher data sets because with a better quality and bigger data set, we'll be able to avoid biases within the data, as overfitting was one of our big issues in making the model. We're also looking into a real-time application where we can look at live video and audio to analyze and test real-time processing capabilities to detect deception. We're also looking into enhancing our data analysis techniques, as our current techniques were mapped for a smaller data set. And once we do find a larger data set, it may not be adequate and it might not be useful for real life use if we do try to have a real-time application of our model. Lastly, we have cross-cultural validation, which is when we basically try to ensure universal applicability of our model by validating the model's effectiveness across different cultures and languages. This allows us to know if our model can be used in any condition, in any scenario in the real world. And here are some of the references we used in our presentation.
And thank you all for listening. And before we finish, we would like to thank our mentor, Bohan, for teaching us and being instrumental to facilitating this project. We would also like to thank Blast AI for the instruction during the bootcamp and continued support with servers, GPU, and a platform. And I know we went just a little over time, but we can now open the floor for any questions.
Thank you. That was awesome. Yeah, 95% accuracy is very, very exciting. In the interest of time, if you have any questions, please send them in the chat. We do want to get on with the presentations. As a reminder to future groups, please do try to keep the time within around 10 minutes for the presentation so that we can have time for back and forth questions. But this was a fantastic presentation. I really appreciate the thoroughness. With that being said, I think we should move on to the next group. Oh, and by the way, if you do have questions, definitely send them into the chat. I think it'd be amazing to have that discussion. But yeah, let's move on to the next presentation, which is streaming pitch estimation using informers. Kyle, are you ready to present?
Yeah, I can start sharing my screen.
Awesome, thank you.
Hello, everyone. First off, thank you all so much for taking the time to be here today. So we would like to give you an overview of our research, which explores streamable pitch estimation using informers. And by the end of our presentation, we hope to provide a clear understanding of how our approach can enhance real-time audio processing. So these are the researchers on our team. We have Ahmed, Sumeda, Kyle, Tanisha, Maya, myself, Katrina, and Sudeep. And our mentor is Bohan, who helped us immensely in this research project.
So pitch estimation is integral to many real-world applications and is a fundamental part of our digital interactions and experiences. It's useful for speech tasks and musical information retrieval, and current methods of pitch estimation have several limitations. They usually require entire input chunks, and they lack robustness against certain types of noises, and they give erroneous pitch values for silent audio. So there's also benefits for streaming, such as noise robust and balanced pitch estimation, which can include more accurate results in noisy environments and lower latency in real-time systems. But improved pitch estimation can help revolutionize our digital experiences and our marketing processes. And the images on the right, the top one is just a picture of pitch estimation in a noisy environment, and the bottom one is just a MATLAB pitch estimate of fundamental frequency.
So in the field of pitch estimation, various solutions and models have already been developed, and they each leverage different techniques to try to solve the challenges of accurate pitch estimation. So here are some of the key approaches. One widely used method is a McLeod pitch method, which utilizes normalized cross-correlation to determine the pitch by identifying periodicity in the signal. The cumulative mean normalized difference function is a method that calculates the cumulative mean or average of the normalized differences in the signal, which helps in identifying pitch by emphasizing periodic patterns over non-periodic noise. The PYN, probability-based autocorrelation, builds on the YIN pitch detection algorithm by introducing a probabilistic framework. It uses autocorrelation to estimate the fundamental frequency, which accounts for the uncertainty inherent in pitch estimation. CREP, which stands for Convolutional Representation for Pitch Estimation, is a deep convolutional neural network with 6 layers that operates on time domain audio signals. And lastly, the RMVPE model, or robust model for vocal pitch estimation, is designed specifically for predicting vocal pitches in both polyphonic and monophonic music. So as Tanisha mentioned earlier, current methods of pitch estimation have numerous constraints which prevent real-time applications. And we understood that exploring and building upon these existing methods would allow us to conduct more efficient and effective research in developing our own solutions for pitch estimation to address these issues.
Okay, so for our goals, we aim to build models with a combination of CNNs or convolutional neural networks, multi-layer perceptions, and informers. And that's in order to find the best way to predict pitch and low latency. And in order to find the best way, we look for the most efficient model architectures that can predict pitch with the most accuracy across various areas, such as noisy environments, and that would make it more suitable for real-world applications. And we hope to do this by enhancing the system's adaptability and accuracy by leveraging the strengths of each model component, aiming to achieve smooth integration into the diverse audio processing tasks. Kyle, you're on mute.
Oh, sorry. So the data that we used for our models were mainly the MRI 1K dataset, which is a dataset of 1,000 song clips with audio and pitch annotations.
We also use the MRI ST500 and MDB STEM synth data sets, but those weren't as helpful as the MRI 1K1. For the preparation for the data, we loaded them and resampled to a consistent 16 kilohertz sampling rate, and we used the pitch labels to provide ground truth during our training and evaluation.
Additionally, we incorporated dynamic batching and a collate function. This dynamic randomized batching ensures that the model is trained on diverse excerpts, making it important for training a better model. And then our collate function, it processes audio samples in batches, then it randomly crops samples to a specified length, and then lastly converts the pitch info into a tensor format. And all of these features enable this function to handle continuous audio data efficiently, making it suitable for real-time applications like streaming.
Okay, since Sudip is not here, I shall continue. At first, we decided to try an approach consisting of a convolutional neural network and an MLP. That way, we decided to try using the collate function first, and then processing data each step to make it streamable. Meaning that, for instance, we take the first 10 steps of time, process it through an MLP, and then concatenate it or process it through a hidden vector and add it to the whole time steps. Then add these features into the CNN plus MLP model. This model, although it got a loss below 1, and it doesn't get the best results in accuracy, which is why we later decided to use Informer. Informer is a transformer-based model optimized for streaming features recognition. It utilizes efficient memory mechanism by reducing computational complexity. Next slide, please. This graph illustrates the CNN plus MLP approach. The main goal, or one of our main goals, was to make the model streamable. But by using that, our model lost a lot of its accuracy, and that's why, even though after applying regularization and dropout of 0.05, our model still didn't get much below the 1 loss, which is depicted here in the average L1 loss difference. L1 loss difference is measuring the absolute difference between the predicted and the true label. And here we can find that our measure is too much, or we lost a lot of data comparing the predicted label to the true label.
So for our informer approach, since informers are trained differently from traditional pitch models, they also predict whether an audio is going to be silent or not, which traditional pitch estimation models often predict like random incorrect values when the audio is silent. We achieved an 82.4% accuracy in predicting silence and an 81.3% accuracy in predicting pitch within 50 cents on the MRI 1K test set. And the model that performed the best was the MRI 1K batch size 64 and Galou activation function with a validation loss of 0.911.
So for our conclusion, our results show that the informers showed very solid accuracy in the low 80% in both detecting pitch and detecting silence, which is very important because in traditional pitch estimation models, they're trained on non-silent audio, which makes them inaccurate if the input given is silent. But our model shows that it's possible to predict both, which better suits real-time applications and real-world scenarios. Additionally, for our CNN and MLP model, it shows that we can estimate pitch more accurately with streaming capabilities. Like it was said earlier, one of the biggest drawbacks of most models right now is that you have to have high input chunks and it's not really able to do it streaming wise. But our CNN and MLP model is able to handle the noisier environments, the different types of audio signals, and higher accuracy, all while being streamable.
So for future work, we can work on optimizing other capabilities. As Maya just said, our model works well in both detecting pitch and detecting silence. So continuing to work on silence detection can be good, as well as polyphonic detection. So handling polyphonic audio involves extending the model's capabilities to accurately estimate pitch in polyphonic audio scenarios, which are just when many sounds are being produced simultaneously. We can also further implement new model architectures to enhance performance and include cross-cultural adaptation, which is just recognizing different sounds, such as other musical genres or languages or specific instruments. And we can also try implementing and testing the model in real-time applications such as live music performances or streaming services.
So here are the key, here are the key sources and research papers that informed our work and provided the foundation for our exploration of pitch estimation technologies. And thank you for your time and attention. We appreciate your interest in our work and are happy to answer any questions you may have.
Excellent job, group. This was awesome. By any chance, do we have any questions from the audience? I guess one question I have is, do you foresee a good pitch estimator being used outside of just recognizing pitches, maybe as like an encoder?
Well, if I may answer that question, it might be possible for language such as Arabic or Japanese, because for these languages, recognizing even words itself is difficult. So if we can improve or add pitch estimation to speech recognition, it will further improve its accuracy for difficult language that has multi-dialects.
Fantastic. That's really cool. If we have any other questions from the audience, please feel free to send them in the chat. This is a really exciting piece of paper. Yeah, thank you. Cool. I think it's time to move on to the final presentation during today's Summer 2024 Symposium. The final presentation's title is Enhancing LLM Conversational Acuity Using Pragmatics Measures. Ignachka, are you ready to share? Awesome.
Okay. Yeah, thank you everyone for taking the time out of your day to see our results today. As Michael just said, we're presenting Enhancing LLM's Conversational Acuity Using Pragmatics Measures by
Andrew Hahn.
Sean K.
Naeem.
Shaurya. Yeah.
Okay, so for an overview of our presentation, we'll be starting off by talking about the big picture and then moving on into the background of what we're doing. Next, we'll go over some goals for the project, as well as our methodology and research process. Finally, we'll look into our results and talk about our conclusion and future work.
Background. AI systems have significantly transformed the technological landscape. With ChatGPT, AI has progressed beyond retrieving information to generating it independently. AI-driven systems can be categorized into two types: chatbots, which provide information and perform specific tasks, and artificial assistants, which use natural language processing and machine learning to learn and improve over time. Our focus on adjusting AI communication styles. AI must be adaptable, using different tones based on social context. For example, it should switch between formal and casual tones depending on situation. Additionally, AI must respect social boundaries, avoiding overly familiar or intrusive behavior while remaining effective and respectful in interactions. To achieve this, we use convergence techniques to adapt communication styles to user preferences, employing metrics like cosine similarity. We also enchain contextual understanding by tolerating response based on specific data.
So big picture, I'll be going over the big picture stuff. So in the landscape of large language models, the challenge of making AI interactions more human-like is crucial. Traditional LLMs often struggle to replicate the intricate writing styles and behavioral nuances of individual users. By addressing these critical gaps, we hope to transform how users interact with conversational LLMs, significantly enhancing the overall user experience and functionality of AI interactions. And for example, like models like ChatGPT 3.0, 3.5 and GPT 4.0 mini have shown limitations when assessed with different tests, and like that shows like their gap in the ability to replicate personal communication styles.
Goals. Let's explore the major objectives of our study. Our primary aim was to condition a large language model to mimic a user's writing style based on their inputs, taking AI personalization to the next level by ensuring the model not only understands what the user is saying, but how they would say it. Personalization was key. We focused on replicating various aspects of the user's writing, such as vocabulary range, sentence structure, and tone, while also incorporating personality traits using the Big Five framework. Our approach was multifaceted. We first created a comprehensive data set of real-world user inputs to train the model. We then analyzed this data to extract linguistic patterns and infer personality traits, which guided the fine-tuning of the LLM. Now, my colleagues will dive into the specifics of our methodology.
The dataset and process. Our dataset is composed of 50 diverse topics, each carefully selected to cover a broad spectrum of subjects. We've included everything from general knowledge and historical facts to more complex concepts like scientific processes and ethical debates. This range ensures that our prompt responses are not just limited to simple factual answers, but also extend to more in-depth explanations, providing a comprehensive approach to each topic. To train and fine-tune our models, we allocated 80% of the dataset specifically for training and the other 20% for testing. We utilize the OpenAI models mentioned before to enhance the capabilities of our system. Our primary goal was to improve the model's ability to capture and replicate user-specific features. This allows us to create interactions that are not only accurate, but also personalized and contextually relevant to each specific user.
So as mentioned before by our teammate, in our methodology, we leveraged the Big Five personality traits to fine-tune the conversational abilities of our LLM. These traits mainly include openness, conscientiousness, extroversion, agreeableness, and neuroticism, which serve as a framework to better understand and simulate human personality. Let's start with openness. This influences the model's ability to be more creative and its willingness to explore diverse ideas. By setting this trait to be pretty high, we enable the LLM to generate more imaginative and adaptable responses, perfect for handling topics that can range from a wide spectrum of subjects. Secondly is conscientiousness. This governs how organized and detail-oriented the model's outputs are. So a high setting ensures that an LLM is precise, reliable, and thoughtful in its responses. Third is extraversion. This affects the tone and the enthusiasm of the LLM. By adjusting this to a moderate level, we were able to strike a balance between sociability and assertiveness, making the LLM engage without totally overwhelming the user or being too reserved. Fourth was agreeableness. This shapes the model's empathy and cooperativeness. We emphasize this trait to ensure that the LLM is supportive, polite, as well as user-friendly. Finally is neuroticism. This influences how the LLM handles stress or challenging questions. By keeping the trait pretty low, we ensure that the model remains calm, reassuring, and emotionally stable in all situations. So through our testing, we identified the ideal balance for each trait, contributing to a well-rounded and effective response from the LLM. This approach not only enhances the model's conversational nuances, but also ensures that the interactions feel natural, personalized, along with being contextually appropriate.
Now let's dive into the quantitative metrics. First, tokenization similarity assesses how closely the tokens in the AI's responses align with those in the desired responses. The cosine similarity is a specific metric of tokenization. It is used to measure the similarity between two non-zero vectors, which in simpler terms means we're looking at the angle between two vectors, where each vector represents a text input, such as the user's response or the AI's response, as you can see on the picture on the right. The cosine of the angle between these two vectors is then calculated, resulting in a similarity score ranging from -1 to 1. A score of 1 means identical text structures, while a score of 0 means that there is no similarity. On the other hand, a score of -1 suggests that the vectors are diametrically opposed, meaning the text structures are complete opposites. Moving on to Jaccard similarity. This metric measures the overlap of words between user responses and AI responses. As you can see in the picture on the right, it's defined mathematically as the size in the intersection divided by the size of their union. In short, it is finding out how many words are similar and how many are different. The score that is calculated from this ranges from 0 to 1, where score of 1 indicates complete overlap, meaning that the tokens/words in the user's input and AI response are identical. And a score of 0 suggests that there are no shared tokens or words at all in both responses.
Our final quantitative metric is edit distance, commonly referred to as Levenshtein distance. This metric quantifies the difference between two strings by measuring the minimum number of single character edits required to transform one string into the other. As you can see in the picture below, these edits can include insertions, deletions, and substitutions of characters. The edit distance can range from 0, where the strings are identical, to the length of a longer string, which represents complete dissimilarity. A lower edit distance indicates a higher degree of similarity between the strings. This demonstrates the model's ability to replicate specific tones, word choices, and writing styles. By integrating metrics such as cosine similarity, Jaccard similarity, and edit distance, we enhance both the accuracy and relevance of AI-driven communication, making it more effective for applications like voice assistants and personalized content generation tools.
Okay, now I'll talk a little bit about our research process. We started off with an initial evaluation of the LLMs. So we created some conversational prompts and then graded the responses off of the Big Five personality framework, as well as those quantitative metrics just outlined. Next, we moved on to data collection. For this, we created a data set of 50 diverse prompts, and for each of those prompts, we came up with original responses that were tailored to address the limitations of the LLMs that we found when we were grading their initial responses. Next, for fine-tuning, we used a standard Google Colab notebook with OpenAI API access. We fine-tuned on the GPT 3.5 turbo model. And as you can see, with a smaller data set of 50 prompts, since LLMs are very good with data extrapolation, we're still able to make a big difference, big improvement in the LLM's conversational capability, even with a smaller data set. And then moving on to testing, we created another set of prompts for validation. For these prompts, we held a direct comparison in the responses between both the original and fine-tuned models. And for this, we included a quantitative and qualitative evaluation. And as for reproducibility, we were able to take that same approach we used earlier and transfer it to the GPT-4o mini model, and we achieved similar results, which Vibha will now talk about.
Yeah, so since we've gone through the basics about the research process, let's just have a quick run through on our results. As you can see, both our models, GPT 3.5 and 4.0 mini, show notable improvements in their fine-tuned responses as compared to their original ones. You can see a consistent increase in the score for the Big Five personality traits. Along with that, the fine-tuning process enhanced the semantic similarity as well as the content overlap, something that can be evidenced by a higher cosine similarity, Jaccard similarity, and a reduced edit distance. So overall, the fine-tuning significantly boosted the model's performance, making the responses more contextually accurate, along with enhancing the LLM's ability to understand the nuances of human conversation and interactions.
Conclusion. All in all, our study shows that fine-tuning LLMs significantly enhances their ability to replicate individual users' linguistic styles and behavioral nuances. Using a mix of quantitative metrics like cosine and Jacquard similarity, along with qualitative assessments based on the Big Five personality traits, we improved contextual accuracy, conversational naturalness, and user-specific alignment. By enhancing LLMs to better mimic human communication, we move closer to creating AI that is not only smarter, but more empathetic.
Future work. In the next phase of our research, we plan to expand our work by applying our findings to multiple languages and dialects, particularly for audio and video inputs. We will also be investigating new methods to further enhance key metrics. By refining these metrics, we aim to boost the model's accuracy and reliability in generating relevant responses. Additionally, we are committed to implementing measures that ensure fair interactions and prioritize user safety. Finally, we plan to incorporate user feedback into our ongoing development process. By listening to the users and making improvements, we can enhance the model's performance and ensure it meets the evolving needs of our audience. Thank you for your time and thank you for listening. We would like to thank all the BLAST members, especially our project mentor, Osher Lerner, and we would like to open the floor up to any questions.
Excellent job, everybody. As always, raise your hand if you have a question. Hey, Osher, super excited to have you here. Go ahead.
Yeah, I would like to ask the team, which part of the research project do you think was the trickiest? Because I know you guys did a lot of research into behavioral science and tried to wield these existing models and fine-tune procedures and a lot of pain points. So what do you think, for someone who's trying to understand your project, what was the trickiest part of it?
I think one thing that we discussed with you as well a lot was the parameters, decide the hyperparameters when we were fine-tuning the model, whether to focus on fairness or uniformity or to focus on exposing the actual strength of the LLM. So I think that was something that we had to discuss and do further research on.
Yeah, that's cool. Definitely tricky. And it's something we're still working on.
Cool. If anybody else has questions, just raise your hand or send them into the chat. This was a really excellent presentation. In the interest of time, I would like to move on to the next section of the symposium so that we don't have you staying back a little too late more than expected. Cool. With that being said, excellent job, everybody. I think we had a real showcase of, fantastic research. I think this is something that everyone who's gone through the program should be proud of. Seriously, I think this is really fantastic. And I think when you finish your papers tomorrow, I think everything you'll be able to look back on with great pride and say, wow, we really did PhD level research and hopefully contributed meaningfully to the field. So once more, let's give ourselves a round of applause. I can't overstate how excellent your presentations were. Cool. With that being said, I think we should transition to the next segment. Arjun, do you want to take away the awards?
Yeah, for sure. Like Michael said, congrats to everyone. We're really excited and happy with all the work you guys did. Without further ado, let's move on to the award ceremony, where we're going to be recognizing BLAST students that have demonstrated great achievement and excellence in their pursuit of pushing the boundaries of current scientific research. And as a heads up, my apologies if I mispronounce any names. If I do, please correct me. Yeah, for the sake of time, we'll go through this relatively quickly. For our first award, we're going to be going through the Excellent Capstone Project Presentation Award. So if you guys remember, and just kind of to give some context for parents and anyone else, so for this award, we want to recognize the great work that our students did during the bootcamp segment of the program. So during the bootcamp, which was the first 2 weeks of the program, the students honed their skill sets and learned a lot of different topics in AI and machine learning and deep learning. and they put them into action by developing an AI capstone project. So these mini projects involve tackling real-world problems with state-of-the-art AI and machine learning technologies. And some examples of projects that students did were using computer vision to solve tasks faced by autonomous cars, leveraging embedding models to solve challenges in molecular science, using sequence-based models to predict stock prices of Fortune 500 companies, and so much more. So some really great stuff. At the end of the project, at the end of the program, the students presented their capstone projects to their peers. And so we want to recognize some of the excellent presentations that we saw in this cohort. So this award goes to Viba Kunchapudi, Ryan Athwal, and Shrey Vishen. Congratulations, guys. Give them a round of applause. And yeah, so great job, everyone. For the next award, we're going to move on to the Resilience Award. So this award goes to students that embody the spirit of trial and error. It celebrates a rugged determination to seek truth and make breakthrough improvements in the world of science. And for this award, we're going to be giving it to Ahmed Sumir, Michael Naeem, and Tunar Mamadli. Sorry if I mispronounced that. Congratulations, guys. Give a round of applause. And for the next award, we're going to be doing the Most Spirited Learner Award. So this award is given out to students who demonstrated intellectual curiosity, passion, drive, and commitment throughout the program. The students that have earned this award are Akshaj Vishnu Batla, Ayan Vaswani, Rithwik Lakshmanan, and Shrey Vishen. So congratulations, guys. Give a round of applause. And for the final award, this is the Leadership Award. This award is given to students who take the initiative to ensure a productive working environment for their team. They would served as a strong role model. They communicated their thoughts effectively and helped rally the team together during challenging moments. And ultimately, they helped guide their team to success. So the students who have earned this award are Shrey Vishen, Abdul Rahman Abdul Wahab, Nashket Bidarkundi, and Andrew Han. Congratulations, guys. You guys did awesome. So yeah, just to kind of wrap things up, we're super proud of all of you guys for your hard work and dedication to really making this program excellent, high quality, and ensuring that everyone had an enjoyable experience. So thank you so much for your hard work.
Thanks, guys.
Really quickly, sorry, I think some people's internet went out for the first set of awards. Arjun, do you mind repeating who won the capstone project awards?
Oh yeah, for sure. Yeah. So for the first award, just to kind of recap, this was the excellent capstone project presentation award. So this was an award that we gave for students who completed the boot camp successfully and worked on a very cool mini project, as you guys might have remembered. And so the winners of this award were Vibha Kunchipudi, Ryan Athwal, and Shrey Vishen. Congratulations, guys.
Great job, guys. Some super impressive work. I'll keep this short, but with that, our 2024 summer cohort for Blast AI is officially completed. And I hope you guys really appreciate how much you learned and how far you guys have come. Let's take a step back really quick and just look at how far we've come over the last 8 weeks. Many of you guys joined this program not really knowing how to code and certainly not being experts or experienced in ML. You made it first through an intensive 2-week boot camp. You built a capstone project, and you just spent the last 6 weeks diving into very, very difficult research. And this is such an expansive field. And I know we've said it multiple times already, but these are real projects. This is real science. We didn't go into a single one of these projects knowing that they would work. In fact, many of them didn't end up working, and we had to make big pivots. But it's just another testament to you guys' hard work and how you were able to adapt to all of the problems and blockers that you faced. Because at the end of all of these 8 weeks, you still all stand here as successful researchers with some truly incredible results. For the last 3 years, Arjun, Michael, and I have been working really hard to build this experience for you guys. And it's built on the core idea that we're extremely lucky to live in a time where we're making tons of breakthroughs every week. A lot of the material that we had in our launch pad and our bootcamp at the beginning, as well as a lot of the research that we did, was built off of updates from the last couple of weeks on archive. Like we're able to adapt and pivot so quickly in this world of AI. And I think it's extremely, extremely incredible that we're able to do that. So me, Arjun, and Michael, we couldn't be happier to inspire the same passion that we had going into this program with you guys here today. It's really awesome that you guys have been able to conduct such novel and impactful research from your bedrooms from all across the world. We had people from so many different countries come together and solve these difficult and insightful problems. And I think that's really incredible and a testament to you guys. So first and foremost, I'd like to thank all of the parents here for giving us this opportunity to mentor and teach your kids. And, the support that you guys give them is very, very noticed. And it's incredibly important to fight through all these frustrating blockers that research presents. We really pride ourselves in giving trust to students to contribute to real science. There are not that many programs that I think high schoolers can join at any stage in their careers and leave as ML experts. People spend years taking college prerequisite courses, and they spend even more time before they get to complete a research projects. And your students did it in 8 weeks. That's really, really impressive. It's incredible to us how your students have been able to deliver on the open-ended questions that we gave them 6 weeks ago. I really hope these presentations spoke for themselves, and you should all be very, very proud of them. Second, thanks to you guys. Thanks to the students. From just coming to the boot camp and asking questions and showing up every single day to leading your own research, and to those of you who are winning awards, being incredible contributors. And some of you guys even becoming the new state-of-the-art models in your fields. We really, really appreciate the effort and grit that you guys displayed this summer. We would not be here today without you guys. I really hope these presentations were impressive and insightful to you guys. Your students became experts in their fields over the summer, and I speak for Arjun, Michael, and I when I say that we could not be more proud of how far they've come. So before we let you all go, this is probably the most cringe thing that we do every year, but unfortunately, it's been a hallmark of our symposiums. So can everyone really quickly turn on their cameras and unmute? And in a second, I'll let you guys know what to do. You guys can just click unmute. It's all good. All right, guys. The count of 3, I'm gonna count down, and then we're all gonna say blast off together. I know it's a cringe moment, but
brother.
let's do it. All right, guys. Let's get all of our cameras on and all of our mics unmuted.
Everybody now.
Everyone here, even the parents. All right. You guys are ready? I'll count down. All right, 3, 2, 1. Blast off.
Blast off.
Yeah.
All right. Thank you guys so much for coming. I hope you guys enjoyed the symposium and watching all of this research. It was certainly very impressive to me, and a lot of surprises here today of the incredible results that you guys had. And huge, huge thanks for you guys for sticking to us for the last 8 weeks. And I hope you guys stay in touch. We'll be sending out a couple more Slack announcements, and I think there's 1 or 2 more assignments. But yeah, great work, guys, and thanks so much for being a part of the journey.
Excellent work, everyone. Yeah, just to recap, housekeeping. Assignment is due tomorrow, Monday, for the paper. Excellent job on the presentations, truly exceptional. I think, I really mean it when you say you blew us all away. And I think parents, thanks again for entrusting Blast AI to educate your students. This has been a journey, and you've come so far. And I think it's safe to say that you're all researchers now. So we're that title proud and loud. And until then, blast off.